All right, class. Today we're going to be looking at hypothesis testing, and this is going to be our last bit of new information for the semester. So let's dig in and see what this is all about. All right, so to kind of describe this as we kind of move through these topics, what I want to do is build this around like a simple case study. And what I've decided to use is this idea, this question of how much water does the average college freshman drink each day? Okay, so let's say that we're trying to answer this study for whatever reason. And there's a few things that you need to do at the outset of each of your studies, okay? The first thing that you need to do is you need to decide what your hypothesis is, okay? And in statistics, we deal and wrestle with two different hypotheses. I think normally if you're used to scientific studies, they have just a lone hypothesis that the researcher is making. But in a statistical study like this, you're juggling two. You have the null and the alternative hypothesis. And with the null hypothesis, we denote that as H naught. That little zero thing means not. And then the alternative hypothesis is HA. And I like to start with HA, the alternative hypothesis, because what the alternative hypothesis is this is the thing that you think is going to happen, right? This would, like in a scientific study, would be just the main hypothesis. So, for example, let's say for our study, let's say that we believe that the average of the population we're looking at, let's say that we think that it's not 0.8 liters, okay? So for our study, we're going to say that we believe that college freshmen are not drinking 0.8 liters a day. Okay, so now with the alternative hypothesis set, right, what we believe is going to happen, right, we believe that college freshmen are not drinking 0.8 liters of water a day. This now sets us up to then set the alternative hypothesis, or the null hypothesis. And the null hypothesis is always going to stand in opposition to the alternative. So for example, with us, since we say that the alternative is that they're not drinking 0.8 liters a day, the null is going to be, we're saying that they are drinking 0.8 liters. And then basically what we're going to do with the rest of the study is we're going to try and take this null and disprove it, right? We want to reject the null. Want to reject this. We want to reject the null hypothesis because if we can reject, then that allows us, if we can, then that allows us to accept the alternative, which is what we're trying to do. We want to reject the null, and if we can, then that allows us to accept the alternative hypothesis. So we spend most of our time focused then on the null hypothesis, trying to reject it. And you'll kind of see how that works as we move through this process. So the other thing that you need to do at the beginning of your study is set your significance levels, or the rejection level, okay? And in statistics, you'll see this signified with an alpha symbol. And there are two kind of industry standard significance levels, 0.05 or 0.01. And what this really means is if you set your alpha or your significance level at 0.05, what you're saying is you're willing to accept a 5% chance or a 1% chance that you're going to reject a correct null hypothesis. Right? What risk are you willing to take? Now, this is you're accepting a 5% chance that you could be wrong, but over here you have a 95% chance that you're right. I mean, and that sounds pretty good, right? Over here, you'd have a 99% chance of being correct. So it all depends on, like, how stringent do you want the limitations on your study to be? For most psychology studies, 5% is that limit that they say, okay, we're willing to accept a 5% chance of being wrong here. Okay. But that's what this is. And you have to set this up before you start the study. You have to make that clear, like what your intentions are. So that's what the significance level is. The next thing to look at is this thing called sampling error. And this is something that in all studies, you can't escape it, okay? So let's pretend that this circle is the population that we're interested in, right? These are all the college freshmen in the United States, right? They're all sitting in here. Every single one of the college freshmen in the United States is in this population because that's kind of how we bound our study. So we know it's going to be completely impossible for us to go in and ask every single one of these individuals how much water they're drinking every day. So the whole point of statistics is we do a study. So I'm going to reach into this population and I'm going to, at random, meaning that every single individual has the same chances of being selected, I'm going to, at random, let's pretend we select 50 of these people. We pull out, okay, so here's my sample of an N of 50. So I pull out 50 of them, and now here's my sample. So the question is, how closely, so if I take an average of this sample, right, equals some number, how closely does this match the average of the population, right? The likelihood of them being the exact same number is pretty small. There's going to be a little bit of variance, right? But based on how much difference there is, that's what sampling error is. There's always going to be some, right? Maybe we'll be really close and the amount of error in our sample will be small. Or our random sample, we may have just pulled numbers that aren't great, right? And we'll have a lot of error. But every sample is going to contain a little bit of error. No sample is perfect. And that's what sampling error is talking about. Is you're going to have to deal with a certain level of error in the work that you're doing. So the sampling distribution of means. Okay, so back to this idea. Here's my population again. And this sampling distribution of means, this is an important concept. So there's the population, and I reach in and I take my green sample. So I pull 50 randomly throughout the population, and there's my green sample. Okay, all of these people go into the green sample. And this is kind of like sampling with replacement, okay? And I put them back, and I go back in and I sample again. I might get some of the people that I sampled in the green, I might get some new ones, but now I build this orange sample. And I put them all back. And then I go in again and I sample again, and I get this new sample. What the sampling distribution of means is, number one, it's really a theoretical distribution that's built from the means of an infinite number of random samples. Okay, so here's mean 1, here's mean 2, here's mean 3. Now pretend I did this an infinite number of times and got an infinite number of averages. Okay, if I take all of these averages, make a huge list, put them in a distribution, that's what the sampling distribution of means is. It would look exactly like this. Okay? It's a theoretical distribution built from the averages of an infinite number of random samples taken from the population, right? So I'm plotting the averages of all of these samples. And again, nobody's going to ever do this. You only ever take one sample. But we need the idea of the sampling distribution of means to do the testing that we want to do. for a couple of reasons. Number one is we don't know what this distribution looks like. It may be crazy looking, right? It could be all kinds of weird looking, but we need a normal distribution to do the testing that we want to do. And the really cool thing is that the sampling distribution of means is, number one, it's always normal. Okay, so that's the first thing that's really cool about it. And the second thing that's important for us is that the average of the sampling distribution of means, right, mu, is always the average of the original population. Okay, so this is equal to the population's average. Every time, by definition. Okay, the way that this is built, the way that it works, the average of the sampling distribution of means is always the same as the average of the population, and it's always a normal distribution. The other thing is that the standard deviation of this thing is, again, it's the standard deviation of the population as well. Okay. So that's what the sampling distribution of means is. And then let me tell you how we're going to use this idea as we move through this study. So if you think back to a couple of slides ago, we said, all right, I have this null hypothesis, right? H naught, and our null hypothesis is that mu is equal to 0.8 liters, right? We think that we want to be able to reject the idea that college freshmen are drinking exactly 0.8 liters of water a day. And so what we need to do is we build this theoretical sampling distribution of means around an average. I set the average of this to be 0.8 liters. So what we want to do is we're going to say, okay, let's pretend that the thing that I don't want is the actual case, that the true average is 0.8 liters. So I can build my sampling distribution around this idea. Okay, and so that's kind of where we're starting. That's why the sampling distribution is important. I'm going to reach back to my alternative hypothesis. I'm going to build this theoretical distribution around my alternative hypothesis. And then the next thing I need to know is, to get the shape of that thing, I need the standard error. I don't know what the standard deviation of the population is, so I'm going to estimate the standard error. And so, right, the standard error is the standard deviation of the sampling distribution of means, and we estimate it with this calculation. I'm going to take the standard deviation of my sample, and then you just divide it by the square root of the sample size. So for us, we're going to take 0.42, which is the standard deviation of the sample that we have. And divide it by the square root of our sample size, so 50. And we find that our standard error is going to be 0.0594. Okay, and so we would use that as the standard error to kind of fill out the shape of the sampling distribution. Okay, but that's the role that the standard error plays. So when you see standard error, it's the standard. It's think of it as the standard deviation of the sampling distribution of means. So back up to this slide here, this thing that we were looking at. We need to know its shape, and so to define its shape, we use the standard error. Okay. So the critical value. Okay. So let's kind of recap to where we are. Here's the distribution I've built. Right. This is This is my distribution. This is my sampling distribution of means. I have set the average of this, and so this is kind of this theoretical thing that we're building. We're saying that the average of this thing is at 0.8, my null hypothesis. And we've set this the standard error. We found that that's 0.0594. And so now we need to find the critical value. Okay? And so if we go back to our alpha, or to the significance level, let's say we use the industry standard of 0.05, or right, that 5% chance. Okay, this is going to tell us what the critical value is. Okay, and we find that by looking at the distribution, and just so in terms of the distribution, we know that underneath the curve, this whole area underneath the distribution represents 100%. Okay? And what we're saying is that we are willing to accept a 5% chance that we're wrong. Okay? So that 5% is going to hang out. Some of it's going to be over here, and some of it's going to be over here. So we take this and split it up into 2.5. Okay, so 2.5% of my error is going to live in that tail. 2.5% of my error is going to live in that tail. That means that 95% of the rest of the area is in the middle. Okay. And I need to know what value marks this line. Okay. And so these are going to be values in z-scores. So right here in the middle is a z-score of 0. If this was one standard deviation, this would be a z-score of 1, z-score of -1. This might be a z-score of -2, -2. What we want to know is, so that's -2, and there's 2. Is for this 2.5%, what's the z-score that represents that little area? And if you go back to the charts, this gives us a z-score of either plus or minus 1.96. So that puts it just right here. Right here. Okay. And so that's the critical value. Plus or minus 1.96. And that marks out all of this area here and this area over here, right? That shows that where that 5% is. And that's going to be really important to us. Okay? So we're building all of this kind of from scratch. So we have our distribution of means that's centered on 0.8 from our null hypothesis, 0.8 liters. And I've now marked out, based on the significance level that I've picked, I have a critical value down here, right? Here's my critical value, which is essentially just a z-score. So here's part of it, and then there's the other part. And then that shows me where the region of rejection is. So this next slide, region of rejection, right? This is just based off of where the critical values are. In the thing that we're just looking at, we have critical values of 1.96 over here and negative 1.96 over here. And so my region of rejection is all of this area here or all of this area there. would be the regions where if my score fell, I could reject. Now, think about this. This is for a 5% significance level. If I bumped my significance level up to 10%, if I'm willing to accept a 10% chance, that's going to kick these areas out and make them larger. Okay? It's going to say, well, I'm willing to accept more risk of being wrong. And the region of rejection grows. Okay? As the significance level, as the significance level increases, the region of rejection also increases. And so do your chances of being wrong. Okay, so let's work this example out from beginning to end. So we're here. We set the null hypothesis. We're saying that they do drink 8 liters of water a day. The alternative hypothesis, the one that we want, says that they don't drink 8 liters of water a day. We set our significance level at 0.5, which gives or 0.05, sorry, which gives us a critical value of plus or minus 1.96. Okay, so that's where we are with all this stuff right now, and then we take a sample. Now you may look at this and say, like, hey, look, our sample had an average of 0.6, and that is not 0.8. So are we done? Can we say with a surety that that this all worked out? Because look, the sample average is not 0.08. Well, that's why that's the whole point of all this, right? We want to test this sample to see if it's a legitimate sample, or a sample that's at least close to what the actual population is. So again, here's our sampling distribution of means. We're going to center it on the nulls, or at 0.8 liters. And we fixed our regions of rejection at negative 1 point, because I don't care if it's below or above. I just want it to not be 0.8 liters. And I went in and I took my thing, and I got an average of 0.6. So I know that I'm on this side of the distribution somewhere, right? I know I'm on the left side of this distribution. So to finish this out, I need to find out, well, what's the z-score going to be? Where is this going to land me in the plot? Okay? And so to calculate a z-score, I'm going to take here's the average of the distribution. Here's the thing that I'm testing it against. So I'm going to take 0.6 minus 0.8. And then normally you would divide by the standard deviation, but because this is a sampling distribution of means, or a theoretical one, I'm going to divide by the standard error. And for us, we calculated that to be 0.0594. And when I run these numbers, I get a z-score of negative 3.37. And that's way out here. Right? This value is way out here. And notice, where am I at? I'm within the region of rejection. So this then allows me to say, oh, I can reject the null and accept the alternative that, yes, college freshmen are not drinking 0.6, or are not drinking 0.8 liters of water a day. And my study leads me to believe that they're drinking less. And notice, that's the claim I'm making. The claim I'm making is that we know that they're drinking less than 0.8 liters of water a day. I'm not making the claim that they are drinking on average 0.6 liters. I'm just making the claim that I know that they're not drinking 0.8. That's the difference with doing studies like this, is I'm not making a definitive claim as to like what is actually happening, but I am saying that I know that it's not this, and my data leads me to believe that it's less. And so that's what this is all about. That's what this testing stuff is all about. Is I set up a sampling distribution based on the hypothesis that I want to get rid of, right? Because the sample that I took, so if you think about how this works, the sample that I took ended up being way out here compared to the average of 0.8 liters. And what this does is think about this in terms of probabilities. What are the chances of me being able to get a sample that's going to be way out here if the true mean is 0.8? And they're minuscule. They're almost zero. For something that has a standard a z-score of 3, we know that anything that's beyond 3 standard deviations away from the mean, you're looking at like the probability of something being out there is less than 1%. So we can say with a lot of confidence that that this is not the case, right? That they're not drinking 0.8 liters a day, that it's less. Now, I made up all the numbers for this just so that we could have like an example to work through everything with. Who knows? Maybe they really are drinking more than that. But this is how this stuff works. So, by the way, what we did was a two-tailed test. And you can tell what kind of test you're doing by looking at your hypotheses, right? So here's H0 and HA. And we set this up to be that the mean was not some number. And then up here, this is that the mean is that number. Because we're just looking at is not, well, that means that it can be greater or it can be less than. If I set this up differently to say, so here's H0 and here's HA. If I said mu is, if I'm trying to say that it's greater than 0.8, so then up here I would still say that mu is 0.8. But now I'm going to put the region of rejection over here. Okay, and this is a one-tailed test. So if your alpha level is 0.05, 5%, now all of the 5% goes into just this one tail. So instead of splitting up 2.5 on each side, this is just that 5%. And notice that from our data, we got a z-score of -3 way out here. Well, that's nowhere near this region of rejection. So I would not be able to reject, in this case, this null hypothesis. And you never accept the null. You always fail to reject. So if I were to report on this, I would say, well, I failed to reject the null, so maybe they are drinking 8 liters a day. But I definitely can't say that they're drinking more than 8 liters a day. We would have to do further studies to refine that more if we wanted to try and make that claim. But yeah, so this is how all this stuff works. This is kind of the culmination of everything that we've been working on and studying this semester. There's a lot going on here. If you have any questions about this stuff, please let me know. Shoot me an email. And we can talk about it. Thanks, everybody. Good luck this week.